5 displacement. We will be able to calculate displacement. Can everyone see this? Can I get a yes from chat whether or not you can see yep, cool. As I said, I say this because I want to make sure that you guys can see it, so I'm not just talking, you know, randomly. All right, displacement. Now we'll talk briefly about displacement because we used that as a bit of an introduction into vectors, but we didn't actually do anything with displacement. So that's going to be what we're going to be doing today, is actually doing some stuff with displacement. So let's talk briefly about what we did last lesson before we jump into what we're doing this lesson. Last lesson that I saw you guys, what we did was we talked about breaking and gluing vectors. What we did was we said, okay, vectors are usually an angle and a size, so like 20 meters north or 30 kilometers up, whereas ij components give you vectors in forms of horizontal and vertical. And we spent the last lesson working out, well, how can you go from one thing, which is like a direction, like an angle and a size, and turn that into ij components? Or how can you take ij components and turn them into a size and a direction? And then we did some examples, and then that was about it. And then I went through the unit circle, and then I gave you guys the last 20 minutes to work on the worksheet. Today we're going to talk about the next topic, which is displacement. Now, the reason we're going to talk about displacement is because you guys might remember this already from from learning about it in science. But in science, I know, at least with my class, if I've got one of my students here from my class, I'm not sure if he's on the Zoom today, but I didn't go through displacement very much. I just sort of said, hey, there's displacement, which is like distance, and then I moved on. So today, though, we're going to, in engineering math, spend a fair bit more time talking about it. You may have spent more time if you did advanced, if you're in the advanced class talking about it, but we'll definitely at least cover it. So we're moving on to a topic about motion. The reason why we're talking about vectors is because vectors is a great way of talking about motion. Because essentially motion is more than just, you know, moving. It's which direction you're moving. And you need to know that for things like trains and planes, where they're moving through, how quickly they're moving. You might think it might be weird that I've got an engine here, but it is engineering. And the reason the engine's here is because there is a lot of moving parts in this engine. In fact, there are probably more moving parts in the engine. Like the engine probably does more moving than the car does overall. And so therefore, you still need to understand the motion of the different parts that make up the engine. And that's, yeah, another part of engineering. It's not just designing. The same thing with a plane. It's not just about designing the whole plane. It's about designing all the things that go into the plane. Even like the airlock for the doors, the window flaps, all of that needs to be engineered, and so it needs to be designed. Right, no pencil here, so you don't need to copy this down. I'm just showing you guys. Now, roughly around the 1600s, Sir Isaac Newton was invented something called physics. Now, that's not to say physics never existed before Sir Isaac Newton. It's just before Sir Isaac Newton, it was usually called natural philosophy. It wasn't called physics. And physics is actually a German word. It wasn't really come up with by Newton, but Newton is said to be in many ways the father of physics. Because what he did was he invented something called Newtonian mechanics. And what Newtonian mechanics is it's based on mechanics. Mechanics is the branch of physics that focuses on motion of objects and the forces that cause this motion to change. Okay, so that's what mechanics is, and that's actually what the word is sort of looking at. Motion and mechanics is this sort of thing. That's also, by the way, where automotive mechanics get their names from. They deal with moving objects. There are two parts of mechanics, kinematics and dynamics. Now, these are going to be two separate topics that we're going to study. First is kinematics. And kinematics deals with the concepts that are needed to describe motion without reference to force. That's what we're going to spend the next probably week and a half on, just kinematics. Okay? Now, when I talk about when we talk about kinematics, we're talking about, well, how can you describe movement? So it's not actually got to do with motion at all. It's just like, how can you describe, if something's moving, what can we say about it? We can say, well, how is its position changing? How is its position changing over time? How is its position change? Is that change in position happening at a constant rate, or is it happening at as an increasing rate? That's what we talk about with kinematics. It's just how are things moving? Is it moving at a constant rate the whole time, or is some of the time it's moving at a constant rate, and some of the time it's not moving at a constant rate, and some of the time it's not moving at all? That's what kinematics deals with. Dynamics, which is something we're going to do after kinematics, which is later on, deals with the effect of forces have on motion. How do forces affect motion? So once we've talked about kinematics, we can then jump in and say, well, how does gravity affect this movement? If I've got a ball that's on a slope, how does gravity, a force, change that movement? How does a magnet change the motion of a nail? That's what we're going to talk about afterwards. So that's how we're breaking this up. We're breaking mechanics, the idea of talking about motion and forces, into two parts, parts without force, parts with force. So kinematics is what we're going to be working on. Before we talk about kinematics, though, we need to get an understanding of the fundamentals of kinematics. The very first one to talk about is displacement. Now, if you don't know, displacement is a vector. And this is something I would like you to quickly write down if you can. Displacement is a vector. It is a vector of the scalar distance. So distance is just a scalar. It's just how far something is moved. Whereas displacement is its vector. Displacement is saying how far something is moved and which direction. Last time we talked about this, we talked about the sheep. We talked about the sheep that moved, if you guys remember, the sheep that moves east, then south, then back west. And you said, well, how is the sheep's how far has it traveled? And we said, some people said, oh, it's traveled 3 kilometers because it's gone 1, 2, 3. Some people said, no, it's actually only traveled 1 kilometer. We said both are correct. We said that the distance traveled is different from the displacement. The displacement needs a vector. Going down this list, we've got speed. Speed is a scalar version. It is how quickly your distance is changing. Is your distance changing slowly, in that you are slowly increasing the distance between you and the object? Or is your speed high? Is that distance increase happening very, very quickly? You're moving away from that object very quickly. That's what we mean by speed. There is a vector version of speed. That's called velocity. That means it's a measurement of not just how quickly you're moving, but which way you are moving. And another example is mass. Mass is a scalar because it's just a measure of the amount of mass, whereas actually weight is a vector. Weight actually tells you which direction. So you really shouldn't be saying my weight is 22 kilograms. You should say my weight is 22 kilograms down. We're going to talk more about weight later on when we talk about Newton's second law. So don't worry about that. I'm going to change the slide. Is that cool with people? Yep, cool. Thank you, Everest. All right, let's jump in. Let's change the slide. It's going to take me ages to learn your names, especially when I can't see you all properly. So we'll definitely, forgive me for not knowing them. This has probably got the most text on it out of any slide that you're going to be copying down today. So if you're like, oh man, there's so much to write down, don't worry, this is the biggest slide. Okay, so distance tells us how far something has traveled. Great. Displacement tells us how far something has traveled, and what way it has traveled. So is it going north, south? Both use the units. What's the units of, just quickly guys, can you help me out? What's the units of distance? Can someone give me a unit? Meters. Is there any other unit that we can use for centimeters, kilometers? Let's put a couple here. We'll do meters, we'll do centimeters. I like that. We'll do one that's not conventional. Let's do miles. I like miles because miles, just because I want to show you guys that all of these are measures of, you could also have feet here, but all of these are measures of distance. It doesn't have to be kilometers, and it doesn't, and not only are these all measures of distance, these are also all measures of displacement, because they both use the same units. Displacement also has a direction, so you might say north, or 20 degrees from the horizontal, or west, or east, or left, or right, or down. You might you might say forwards. You might say the displacement of this car is 20 meters forwards, 20 meters backwards. Doesn't matter, as long as it's got something to signify a direction, then it's a displacement. And it has the symbol X. I will warn you, I made a mistake with because I'm teaching you physics for the first time. It doesn't always have a symbol X. You can sometimes use the symbol S. The reason I've made a mistake is because I've started to teach physics, and they realized the book, because I couldn't see the book when I was teaching year 10 engineering maths, the book uses S, and I'm like, crap, I've got to change everything. I'm not sure, I might change it here as well. So we might use the symbol S instead of the symbol X, but at the moment, even if we do use the symbol S, it's important for you guys to understand that you can use both. Now you might be saying, okay, sir, great, but why don't we use D for displacement? D for displacement makes sense. And you said, I would say, yeah, I would agree. Does anyone want to give a suggestion why we don't use D for displacement? D stands for what? Direction? No. D usually stands for distance. Thank you, Dylan. Usually D stands for distance. And so that's why we don't use D for displacement, because we don't want to get them confused. That's why I usually use X or S. The reason why we use X sometimes is because mathematically we always use X for an unknown. And so if you end up doing specialist maths, they use X. S, I don't really know why they use S. I'm also a bit like, why would you use S? It's going to get confused with speed, but that's just how that's just what they do. So yeah. Let's go with, okay, so I'm going to change the slide. Can I change the slide yet, or are people still writing this slide down? If you weren't aware that you have to write it down, then I'll give you guys a chance now to quickly take some notes. I might give you guys 30 seconds from now, and then I'm going to change the slide. Okay, so let's jump on. Let's keep going. So yeah, that's what displacement is. Distance, displacement. Cool, perfect. What else have we got? So the next slide I like gives a bit of a difference between distance and displacement. So I like this picture, and the first time I put it up, I got the maths wrong, but I've fixed it now. Let's grab a look. Let's just say you've got a start and an end. Yeah, we're going to draw and this is the same thing that very similar thing to the sheep. Let's say that we move that I run 2 meters north, then 4 meters east, then 4 meters south, then 1 meter east, then 1 meter south, 2 meters west. So that gets me to the end. Okay. Now, if I did this big long journey here, I could then find out my total displacement, distance traveled, by adding each of these. 2 plus 4 plus 4 makes 10, plus 1 makes 11, plus 1 makes 12, plus 2 makes 14. The distance that I've traveled is 14. But how far have I traveled from the start? How far have I actually moved overall? What is my displacement? Well, to work that out, you really need to get this length here and this length here. Now, if you wanted to work out what the distance was, I'm going to try and do this with a pen. It's not going to look nice, but yeah. If you were to work out how to get this 3, I would actually do it like this. You've got a 4 here. So if I was to go like, let's just say I was to take east as being positive. I'm going to go east is positive. You're going to have to deal with my bad writing here. We've got plus 4. Okay. Man, I wish I had my thing. Then here, I've got another one that's still going east. So I've got plus 1. But then I've got a west movement. Now that west movement is in the opposite direction. So I'm going to write a minus 2. That means my overall direction is 3. And not only that, it's plus 3, which means we're moving east 3, which is how we got this measurement here. As for south, we've got 2, we'll go with this. We'll go with, let's say north is positive. That means we've got 2 north, so we've got plus 2. Then we've got 4 south, so we've got minus 4. And then we've got another 1 south, so we've got minus 1. Which means overall, we have -3, which means we're going 3 south, which is how we get this measurement here, 3. Just in case you were like, oh, okay, you know, I don't think you were necessarily going to be concerned, but you might be like, how does this work? How do you figure this out? So you could just, of course, just logic it out and just be like, oh, well, I can see that it's 4 across, but then I come back, I go 5 across, but I come back 2, so that's going to be 3, the difference. Yeah, sure. So that means the displacement is going to be the square root of 3 squared plus 3 squared, the left squared plus the right squared, to make the final length of this Pythagoras side. Happens to be the square root of 18, which is 4.24. Those of you nerds that are coming from advanced maths and like thinking, oh, well, we could just call that, 18 is just 2 root 3. Yeah, you could, but we're not going to do surds in this class. We're just going to approximate things. If you have no idea what I'm talking about, don't worry. 4.24 is an approximation. That's pretty good. Now, because this measurement and this measurement is the same, I can write 45 degrees south of east. It's actually a really bad way of writing down a direction because you're saying, oh, I'm starting at east and I'm going south. What you really should do, like what the direction that we really should give is all of this. So you would say, I would probably say either 135 degrees true. Or if you are going to use bearing like that, you would probably draw a line here and you'd say, oh, well, that's going to mean that that is south 45 degrees, 45 degrees east. Oopsies, that's an E, okay, trust me. Oh my God, that's an E? Yeah, we're just gonna pretend that that's an E. Jesus, true bearings. You could use a true bearing. The one on the right, this is the true bearing here. This one is another way you could do it, south 45 degrees east. Oh my God. This is not an ideal way, but it still works. It's still a direction. Yeah, so that's displacement versus distance, okay? Displacement is, you can see that we've got to give a direction and a size. Now, I've got a question for you guys. I'm going to give you guys a minute to answer these two questions. You can copy this down. You can just write down the answer. I don't care. But I'm going to give you guys a minute from now to answer this question. Starting from the origin, a person walks 90 meters east, then turns around and walks 40 meters west. What is the total walk distance? What is the displacement? I'm going to give you guys a little bit of time to work on that, and then we're going to do it together. Yeah, that's right. I'm giving you guys a little bit more time to answer this. All right, boom, let's do this. So Everest is given an answer a little bit ahead of time. What is the total distance traveled? Well, we went 90 meters east, then 40 meters back west. Total distance walked is 130 meters. Has someone else got the, what's the displacement? How far away from, how far have we traveled from where we started? Who's got the displacement for us? Come on, throw it in chat or wherever. $50 east, let's have a look. Yeah, I would say it's 50 meters east is a little bit better. Thank you for that. It is 50 meters east. Now the trick for that would be to say, let's just make, how would you do it? I would say, let's make east positive. So that means we're moving 90 meters east, so we've got plus 90. And then we're moving 40 meters west. So that's plus, because it's plus negative 40. And if you add negative 40 to 90, you get positive 50, which means it's 50 meters east. Perfect. Now, that positive means that it's going east. So that's how I know. Now I'm just looking at my watch now, and realizing that we're pretty much out of time. Let me just check. I want to quickly check how many slides we had left. We just have one slide left, which was a bit complex. So I'm going to leave that till, not complex, but something, whatever. I'll leave that till tomorrow. We'll do this one tomorrow at the very, very start. before we start moving on to displacement time graphs.